So let's think about those steps with kind of a picture here. Here was our enzyme ribbon molecule. Here it is with each of those active domains shown with just a box. Okay, so we have the orange one, the orange one, the yellow one, the yellow one, and so on and so forth. Okay, and then here's our acyl carrier protein. So this is what we're looking at. And let's step through all those stages. I know it looks like a lot, but we're going to step through it one at a time. Okay? So in this first box, when we first start, we have our acyl carrier protein, and it has that acetyl group bound. Okay, so if you remember, we had the, let's change color here, we had that transacetylase enzyme that transferred the acetyl group to that carrier protein. Okay, so essentially we're now all loaded up with our acetyl group. We're ready for a reaction to occur. What's going to happen is that this carrier protein, this swinging arm, is going to pull it up here, and it's going to pass that acetyl group off to the docking site. Whoops. Okay, so when I do that here, I've now kind of temporarily stored that acetyl group up here. So I passed it off to the docking site, and that allows my carrier arm to pick up that malonyl group. And remember, that will have my CO2 minus my carboxylate group here. So now we have both of these things near each other. All right, and then we're going to see a condensation reaction occurring. All right, so what's going to happen is the acyl carrier protein is going to essentially bring these two pieces together in the active site, okay, of that KS one. And when it does that, all right, they react. We get that condensation reaction. We see a carbon dioxide gets, oops, I should draw that a little somewhere else. We're going to see a carbon dioxide get split off. Okay, and when I look at that now, those two have combined. So I've got my molecule. So now I've got 4 carbons, right? I've added 2 carbons to this growing chain. Okay, then what it's going to do at that point is it's going to swing it around to the KR active site. Okay, so it's going to take this whole thing and pull it around to the KR active site. Now that it is formed in the KS active site, now it's in the KR active site. And when that happens, it's going to be reduced. All right, so we have a reduction reaction here. It should say right there. So this is going to be a reduction reaction. And so when we see that, now we have our Oops, not there though. We have our carbonyl. And then we've got, but this carbonyl has been reduced. So that has our OH, okay? And then what we see, right? So now it's going to take my swinging arm is going to take it and pull it down into this active site once it forms. All right, and at this point, the water is going to peel off from the alpha and beta carbon and leave us with a double bond. All right, so this was our dehydration step. So if I think about what that's going to look like, I'm losing a water. I'm going to form a double bond. Actually, well, I think I'm just thinking about the best place to draw this so it'll all fit. So we've got S, our sulfur. We've got our carbonyl right here. And then we've got a CH and a CH, and then our CH3. So now we have that double bond. Okay, that carrier protein is going to swing that thing around now that it's formed into the active site of the ER1. Okay, and when that happens, hydrogen's going to get added in across, so we're going to have a reduction reaction. And hydrogen, H2, is getting added across that double bond to give us this saturated little acyl chain. So now, if I look at it, I've got my sulfur, my carbonyl, all right, and then I've got CH2, CH2, CH3. Okay, so as we're doing this, as we add electrons, something kind of key to note is those electrons for those reductions are being added by the NADPH, right? That's what we need for those electrons, even though we're not showing them in here. And then what's going to happen is this acyl protein is going to move, this acyl carrier protein is going to move this whole thing back up to our docking station. All right, so we're going to come up here and we're going to move this now much longer protein, or much longer molecule back to that docking station. And what that does is it lets it come back in here and pick up another malonyl. So we've got and now the cycle can start all over again. So essentially, we are building these up 2 carbons at a time. So the next time we circle around, this will be 2 carbons longer. The next time we circle around, that will be 2 carbons longer. If we look at the overall process, okay, it takes a lot of stuff to do this. Okay, when we look at this, the palmitate requires 8 acetyl-CoA, 14 NADPH, and 7 ATP. All right, this is not easy. Like, we're using a lot. If we look at the stoichiometry for the synthesis of palmitate, that whole cycle we just went through, we needed 1 acetyl-CoA to start, and then we'd have to go through the cycle 7 times. So we're every time, remember down here at the end, I picked up another malonyl. So when I do that, I need 7 of those because I have to go through this 7 times to get up to 16 carbons because the first round gets us to 4, right? Okay, 14 NADPH, H plus. And then to kind of remember that we need 7 of these, but we have to make those from the acetyl-CoA. So our net overall reaction requires 8 acetyl-CoA, all right, from our very early starting material. You'll notice the malonyl-CoA cancel, so do the carbon dioxide. We end up with this palmitate, which has 16 carbons, so 16 carbon, and each cycle has 2 reductions, so we need 7 cycles, hence why we need the 14 NADPH. All right, so what we want to look at is this kind of comparison now between this beta oxidation, the degradation of fatty acids shown with the pink on the left, and the synthesis shown in the blue on the right. Okay, these are really, really similar. The substrates are the same. Okay, so we have the same substrates except that the carrier for our beta oxidation step, the carrier is that coenzyme A. And if we're on the synthesis side, that carrier is that ACP, that acyl carrier protein. Now the enzymes are different because we're doing different things. This is reciprocal, it's tightly controlled. So if we let's just recall, beta oxidation. We're going to come in here, we have our molecule, we're going to break down. It's got a CoA carrier. We are going to oxidize it at first. We get that double bond. Okay, so we have that dehydrogenation, we have this oxidation step. We get the double bond. We're going to add water across the double bond to get that OH. We're going to oxidize it to get our carbonyl. All right, and then we're going to have the sialytic cleavage to break off that acetyl-CoA. Okay, and leave us with a smaller molecule, which then we'll start with again going down. So we made it smaller, 2 carbons at a time. Looking at it in reverse now, starting with a small molecule, right, the acetyl and malonyl, we're going to start with this condensation. Okay, so we're adding the 2 together to make it bigger. Then we're going to reduce it, so we're going from the carbonyl to the OH. Okay, we have a dehydration, so we're pulling that OH and H off and getting our double bond. And then we're reducing it. We're adding electrons across that bond to get back there. Okay, so the water will be the same, but it's added here, removed here. Our electron carriers, NADH and FADH2, but over here on the right, they're the NADPH. So similar, but with differences. All right, think about this. What are the raw materials for fatty acid synthesis, and how are they obtained? So pause the video for just a sec and stop and think. What did we need to get this started? All right, hopefully you paused and thought about that. We need acetyl-CoA. Okay, we get that from pyruvate, which came from the glucose or amino acid, some carbon source. We need malonyl-CoA, okay, our activated form. We got that from the ACC1 catalyzed, so that enzyme catalyzed reaction of acetyl-CoA. So we need both acetyl-CoA, but then we also need this activated version. And we need that NADPH. Remember, we had to utilize some from the pentose phosphate pathway. Okay, so this fatty acid synthase can get us up to 16 carbons, but if we want longer chains, your body can do that, but not with the fatty acid synthase, okay? So longer ones are synthesized by enzymes attached to the endoplasmic reticulum, and they add 2 carbon units at a time using that malonyl-CoA as a substrate. So essentially, we can make them longer. It's with different enzymes. And then if we want to talk about making unsaturated, so the fatty acid synthase made saturated, but we can also introduce double bonds. So once we make the saturated fatty acid, we can introduce these double bonds to make it unsaturated. Mammals lack enzymes that introduce double bonds beyond carbon 9. So if we take a look at these two, so linolenate and linoleate. When we look at these two, these are two what we call essential fatty acids, because take a look at where their double bonds are. When I look at this, so omega 6 and 9, remember omega counts from the end, so 1, 2, 3, 4, 5, 6, 7, 8, 9. But when we just label these beyond carbon 9, we're talking from this side, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So our body cannot make this, okay? It's too long with double bonds too far from, really, that's it. Double bonds too far from the carbonyl carbon. Same with this one. Hence, these are things that have to be obtained in your diet. Your body cannot synthesize them. All right, we are done with this video. Go back, review those steps. I know it was a lot, but we went through it 3 times. So sit down and think about how that swinging arm carries things from one piece of the enzyme to the other. And then think about what's happening at each spot.